In this lecture, we'll discuss the Paxos algorithm. Paxos is a distributed consensus algorithm that was proposed more than 20 years ago, and henceforth, many avatars of Paxos have been proposed. So, we will be looking at something called Paxos Made Simple, which is a simplified explanation of Paxos, which was published later, roughly in 2001. So we'll first discuss the problem of consensus, which is a very, very important problem in distributed systems. And then we will discuss the Paxos algorithm and finally prove it. So the problem of consensus is very simple. So it is like this, that we have a multitude of processes. And so we have different processes, right, over here. Each process may propose a value. So the processes coordinate among themselves to agree upon one of the proposed values. So let's say that this process over here proposes 3, this proposes 4, 5, 6 and 8. So then these 5 processes coordinate among themselves to agree upon one of the values that has been proposed. So kindly note that the value that all the processes agree upon has to be one among the proposed values. So it's not the case that all of them can agree upon value 0, because value 0, it is true that all of them would agree on the same value, but the value of 0 has not been proposed. So this criteria has to hold, that the value v has to be proposed by at least one process. So why is the consensus algorithm so important? Well, so the reason it is that important is basically because in a distributed system, the main aim is that we want the entire system to look like a single system to an outsider, which means that between the different nodes, there has to be a notion of an agreement, that they agree upon something such that that agreed value can be showed to an outsider. So let me give one example. So one example in this case would be that of somebody trying to buy an airline ticket with a credit card machine. So we have different processes. So one process, of course, is the user. One process is the credit card machine. One more process is the credit card company. So let me call it the CC company. Then if I'm using a online booking site like Make My Trip, Expedia, that would be one more entity. So let me call this the site. Then of course we'll have the airline. Once the ticket is booked, I get an email with my e-ticket. So then of course my email is one more process. So how many processes do we have? We have 1, 2, 3, 4, 5, 6. So if I book a ticket, all 6 of us have to be in agreement about 2 things. Either the ticket is booked. So if the ticket is booked, well, then the machine validates my credit card, the money is debited from my credit card, it goes to the site, and then the airline books the ticket and I get the ticket via email. If let's say the ticket is not booked for some reason, then also there is no problem. I am duly informed that my ticket could not be booked. The problem arises when let's say that I book a ticket for 10,000 Indian rupees. So then, 10,000 rupees get deducted from my account and the ticket is not booked. So this has happened to all of us. It has definitely happened to me a lot, that my money was debited, but my ticket was never booked. And so then I had to keep on calling the site of the travel agent, the online site, and they would, they would say that all is well, whereas all is not well. And because I don't have my ticket, and the main problem is that there was no consensus among these 6 sites. Had there been a consensus among these 6 processes, then this particular problem would not have happened. So either all of them would have said that my ticket is booked, which means I would have had my ticket with me, or all six would have said that for a certain reason they were not able to book my ticket, which is also fine by me, but I don't want an intermediate situation. All right. So this is the example that we gave is essentially a commit abort problem, where I say that commit means that my ticket is booked, and abort means that my ticket is not booked. So all of us have to agree on one value. And well, there can be many other examples of a consensus. So that can also be where I'm doing distributed computation, and so then I need to ensure that all the processes get the same values, and also others. So we can say that what is the big deal with consensus? It's very simple. We can elect a leader. We already have many algorithms to elect a leader. We use the leader to collect proposals, decide on a consensus value, and broadcast it to all processes. This seems to be a very fair idea, where we have a set of processes. They elect one leader among them. All the processes send their proposals to the leader. The leader chooses one and distributes it back. Well, this sounds to be a good idea. The only problem is that if the leader fails, then there is an issue. But then, of course, we can say that we can elect one more leader. Sadly, there is also an issue with that. And so we'll see that on the next slide. And also the philosophical issue with this algorithm is that in a certain sense, we are centralizing the distributed algorithm, which in a certain sense also violates the spirit of distributed computing. In distributed computing, the main idea is to increase throughput by allowing multiple servers, multiple processes running on multiple servers to do the job. So why is this consensus problem that interesting? Well, because we are going to consider faults, and that is because faults always happen in the real world. And also, see, the reason that I was not able to book my ticket in many instances was basically because there was a failure at some point. Either there was a failure in the network, or there was a failure in the credit card authentication process. So these failures are what give a real world feel to the problem. So now let me come back to what I said on the previous slide number 4, that we can elect a leader. The leader can choose one of the proposals. So there is a very famous result in distributed systems called FLP result, which we have already discussed in the class. So this says that it is impossible to achieve consensus where even if we have one faulty process in an asynchronous system, it is not possible to achieve consensus. So what again is an asynchronous system? It is a system where the processes do not have a shared time base, and they are not obliged to give a reply within a certain period of time. So that is an asynchronous system. So here, if we have a faulty process, so of course we have no way of distinguishing between a faulty or a failed process and a slow process. A consensus is not possible. So of course we had a long and elaborate proof. So if I were to just take the gist out of that proof, the gist would be that let me assume that I have 2n plus 1 processes. Let n processes propose 1 and let n processes propose 0. So one of the 2n plus 1th process essentially holds the key. And this is where the algorithm can get stuck forever, because we'll never know what it decided. And this is essentially why the problem of consensus becomes that interesting, even when we consider faulty processes. So now the choices in front of us are reasonably stark. We know that because of the FLP result, we cannot devise a consensus algorithm where even one process is faulty. But well, faults are a part of real worlds. So should we then abandon our efforts? Well, the answer is no. Instead, we look at what exactly we want. So we need to prioritize, right? So when we know that we can't get all of it, at least we should be happy if we get some of it. So what is that? So we can look at the safety property and the liveness property. So the safety property says that something wrong does not happen. So consider a traffic light. If one of the roads is green, right? If the lights for one of the roads is green, then we don't want the light on the other road to also be green. Otherwise, there will be a collision. So we want the lights on the perpendicular road to be red. So this is a safety property. The other is a liveness property, which says that something good always happens, which means the red light over here will ultimately turn green. So whenever we are looking at a protocol, we would ideally like to have both, but now we know that it's not possible to have both. So the FLP result clearly says we cannot have both. So if we cannot have both, let us have protocols that never violate the safety property, which in the case of consensus would mean that the key assumptions of consensus, which is that choose one among the proposed values and everybody agrees on the same value, this should not be violated. But liveness in this case would be that the algorithm always terminates and always is successful for all processes. So let's assume that we are not concerned about liveness, which means that there will be cases in which the algorithm will not terminate. So let's just live with safety alone and propose the Paxos algorithm that satisfies the safety property. So coming to the Paxos algorithm, we have three kinds of nodes. So a process and a node we will use synonymously. So we have a proposer. A proposer is one that proposes a value. Then we have an acceptor. So acceptor is a set of nodes. So this that accept proposed values. So here accept is a temporary acceptance. It's not a permanent acceptance. It's just a temporary acceptance, which means that it records the value that is being proposed. And then, so we have three levels essentially of a proposal. We first propose the proposal, then we send it to a set of acceptors where they can temporarily accept it. And finally, when the consensus is done, we call this choosing. So choosing means that a value has been chosen and consensus has been achieved. So accept is a path in the middle where a value is just temporarily accepted or buffered. Then we have a learner. So learners are nodes that join the consensus protocol late and they want to learn the value that has been chosen, right? They want to learn the value that has been kind of accepted by everybody. So note that a node can be a proposer or an acceptor at the same time. And so it's not that, we have designated nodes that are proposers and designated nodes that are acceptors. So the main motivation of the algorithm actually comes from several of these conditions that we will name C1, C2, C2A, C2B, etc. So let's outline these conditions. The first condition is called the first accept condition, condition C1. See, if I am an acceptor, I do not know how many proposals are there in the system, right? So any node in a distributed system always has a very local view. So it does not know how many proposals are actually floating around in the system. Hence, the only option or the only choice that an acceptor actually has is to accept the first proposal that it gets, right? So it has no other choice. So this is pretty much the best that the acceptor can do, is that accept the first proposal that it gets. Subsequently, it can become more choosy, but at least the first proposal it needs to accept. So now several values can be proposed by different proposers, and different acceptors could accept different proposals. So then the problem is we will have a situation in which our acceptor nodes are sort of sitting there with accepting different proposals, P, P dash. It is furthermore possible that because of this, but finally, something has to be chosen. So we will find that it will become necessary for an acceptor to actually accept multiple proposals and then ultimately do something such that one of them is ultimately chosen as the consensus value. And so we will see that each proposer, after several rounds of messages, will ultimately need to choose a consensus proposal, and we will see how that will happen. But the important point in C1 that I would like to make again is that an acceptor has a very local view, an extremely local view. So the first proposal that it gets, it needs to accept, and it also needs to accept many more proposals after that, primarily because you'll have other acceptors that have accepted many other proposals. So the model that I'm talking about is that you have different proposers that keep proposing, and you have a set of acceptors that would be like buffering a subset of the proposals that it gets. And ultimately from this subset, one will be chosen. We will see how. So every proposal is a tuple, is a two tuple, number and value. So all the proposal numbers we assume are unique, and it's not required, but it would be good to assume that they are also monotonically increasing, at least from every node issues monotonically increasing proposals. So mind you, this is not required, but this will make our job easy. How do we ensure that the proposal numbers are unique? Well, this is also easy. We can assume that they have it's a tuple of a PID and a local counter. And so we have already seen this in the case of local Lamport clocks, that with a combination of the process ID and a local counter, we can generate unique numbers. Furthermore, each proposal proposes a value, and one among these proposed values needs to be chosen. So we will assume both of these are integers. So the consensus condition is that if a proposal n comma v is chosen, then every proposal with a number greater than n that is chosen has to have value v. So this is the consensus condition which we will prove, that the moment we have chosen a proposal with a certain number, then every subsequent proposal that is actually chosen by the system. So we will see that we can choose multiple proposals, but all of them have to choose the same value v, which means that this value v becomes the consensus value. So this is sufficient to satisfy. So condition C2 is sufficient to achieve consensus. So which is, reasonably clear that the moment we have chosen one value, any higher numbered proposal issued by any process, doesn't matter, has to again end up choosing the same value. So we can now further kind of specialize condition C2 to condition C2a. So we'll propose several specializations. The first specialization is that if a proposal with value v is chosen, then every higher numbered proposal that is accepted by any acceptor has value v. So what this essentially says is that if a proposal with value v is chosen, after that, of course, still nodes can keep proposing, still nodes can keep accepting, but the acceptors are now bound by value v, so they are not going to, for any higher numbered proposal, accept any value that essentially does not have value v. So here the explanation is that assume that a process wakes up and gets a proposal. By condition C1, it needs to accept it. This is clearly not desirable. Hence, to ensure condition C2A, we have to strengthen C2A such that it will simply not accept any proposal that doesn't have value v. So the way that we want to ensure condition C2A is by proposing a condition C2B, which will essentially ensure condition C2A. So C2B, this is what it says, that if a proposal with value v is chosen, so assume that a certain proposal, right, with value v is chosen, then every higher numbered proposal that is issued by any proposer has to have value v. So we are further tying up the system. We are saying that, look, once something has been chosen, then subsequently, if any proposer is issuing any proposal, right, then that also has to have a value v. So this is a reasonably strong condition, but let us look at the implications of this. So the implication of C2B is that it automatically implies C2A. That, look, since a proposal with value v is chosen, every higher numbered proposal accepted by an acceptor also has to have value v, because the only v is being proposed, nothing else is being proposed, right? So if you look back at C2B, just take a look at this line. So what I'm trying to say over here is the moment that a proposal is chosen, any other proposal proposed by any other proposer, subject to the fact that that proposal has a higher number, it has to propose the chosen value. We will see how to ensure that. But assuming C2B is ensured, it is very easy to write this expression that C2B would imply C2A, which is that any acceptor has to accept only value v. Well, that is clear because only value v is being proposed. And then essentially C2A would further imply C2, that since only value v is being accepted, ultimately value v will also be chosen by a higher number proposal. So what did we do? We wanted to ensure C2, right? To ensure C2, we tried to ensure C2A, right? Ensuring this will ensure this. To ensure this, we created a C2B. And so if we can ensure C2B, it will ensure C2A, which will ensure C2. And then we have said that if we can ensure C2, then we can ensure consensus. So that is what our claim is. So these conditions C1, so what did we do? We had a condition C1 and then we had C2, which of course, we had these sub conditions. So this is reasonably complicated. So I would advise the listener of this video to go through this several times and to also read this in the paper, because appreciating this part is reasonably tricky. And this is probably why many people have had a lot of problem with the Paxos algorithm. But once we go through the algorithm and the proof, these assumptions, the need for these assumptions and these conditions will become clear. So where were we again? So condition C1 was, let's go back and see that. An acceptor doesn't know how many proposals are there in the system. Hence, the acceptor must accept the first proposal that comes by its way. So this is that you accept the first proposal you get, and furthermore you have to accept a few more to actually complete the algorithm. Condition C2 was that a value V has been chosen by, right? So condition C2 over here was that if a certain proposal NV is chosen and in NV value V is chosen, then any higher number proposal whose number is more than N, that essentially has to choose value V, that essentially has to accept value V, that essentially has to propose value V, right? If we can ensure these things, we can ensure consensus, and how to do that is what we will see in the algorithm. So the Paxos algorithm is divided into two phases. So they are known as phase 1 and phase 2. So the algorithm might seem simple, but it is in the category of deceptively simple algorithms, where even a very simple algorithm is reasonably hard to prove. So the first we start by sending a prepare message to a majority of acceptors. So it is assumed that the size of the network is known. So to a majority of acceptors, we send a prepare message. The other very important point to note over here is that in the prepare message, we only send the number of the message number, which is assumed to be unique. So no two messages will have the same number. So we are not sending the value. This is important, and we will see that this will be useful in proving condition C2B, which essentially means that the proposer is not at liberty to propose a value. All right. So the proposer is basically dependent on other factors to propose a value. And this liberty of proposing any value that the proposer wants to propose is at least not there with the proposer in phase 1. In phase 1, if we look at line number 2, the prepare message is sent with just the number of the proposal. That's all. So every acceptor maintains two state variables. One is max prep and the other is max accept. So max prep is the largest number that the acceptor has received as a part of the prepare message. So every prepare message sends the number of the proposal, and the largest such proposal number that has been received by an acceptor is called max prep. So this is accepted. The prepare message is accepted by an acceptor only if n is greater than max prep. So mind you, n cannot be equal to max prep because message numbers are assumed to be unique. So only if n is greater than max prep is the proposal accepted. Otherwise, we can add an else over here. We just don't do anything. We just ignore and nothing goes back to the proposer. Or we can send a NAC, a negative acknowledgement, saying that this proposal has been terminated. This proposal has failed. So assuming it is accepted, we set max prep to n. So this always monotonically increases. And we return the value of max accept. So max accept is essentially a value, right, which currently the acceptor has accepted. So why the max comes in max accept will be clear in later slides. But let's say that at the moment, all that we can say is that max accept is the value that the acceptor has accepted. So in fact, if it is given a choice of values, it has taken the maximum. That's where max comes from. But for let's assume that for the time being, If the prepare message is accepted, then the currently accepted value is sent back. So now let us look at, so once it is sent back, we look at phase 2. So let's say phase 2 starts from here. So the end of phase 1, what happens is that we have the proposer here. And we have multiple acceptors. So they first got a prepare message. So then they are supposed to, if it passes phase 1, they are supposed to send a message back. And the ith acceptor will send back the value of max accept I. So on similar lines, the rest of the acceptors, so you're assuming the rest of the majority acceptors will send back a max accept message. So what the proposer will do is that after it gets back all of these max accept messages, it will compute the maximum of these messages, right? So it's essentially, it will find the maximum value out of these and assign it to a variable v. So it is important to consider what happens at the time of initialization. So I have not mentioned this, but this is a side note. So the variable max accept and max prep both are initialized to the null value. You can assume that if all the values and proposal numbers are positive, this can be -1, or it's any other value that indicates that it is null. So when we are starting phase 1, which means at the time of initialization, all the max accept values that will be sent to the proposer, all of them will be null. So then we can add an extra line over here, which is basically over here, just after this, that after this, if all of them are null, then the max of all the nulls will still be a null. So if v is equal to null, then essentially we set v equal to a proposed value. So what this essentially says is that if v is equal to null, which means that if all the acceptors send a null value, then the proposer is at liberty. This is the only time when the proposer is at liberty to actually propose a value on its own, which would be, the value that it would have, it wanted to propose. But it is important that it does not have this liberty. It gets the freedom only when all the acceptors return a null value, and then the proposer proposes a value and sets it to v. Otherwise, it needs to take the maximum of the values that it has gotten. So after that, we send an accept message. So this time the message has the number and the value, quite unlike the prepare message that did not have the value. So we send an accept nv message to all the acceptors in the quorum, and that begins phase 2. Alright, so the phase 1 messages were the prepare message and the response max accept message, and we begin phase 2 with the accept message. So we begin phase 2 over here. With the accept message that is sent from the proposing node to the accepting node. So phase 2 also works on a similar manner. So in this case, if n is greater than equal to max prep, So note the equal to, well, the equal to comes because of the following reason. So the first we send a prepare message. Then, so this is phase 1. Then we send an accept message, assuming it passes phase 1. So in the middle, if there are no higher numbered prepare messages, then in this case we set max prep equal to n, and max prep maintains its value till this point, till the accept point. It maintains its value. So in phase 2, we might very well find that max prep is equal to n. It might be larger also. So if it's larger, then what does it mean? It means that another prepare message came with a higher numbered proposal. So in this case, of course, phase 2 fails. Otherwise, phase 2 passes. So if n is greater than or equal to max prep, which basically means that no higher numbered proposal has come in the middle, then phase 2 passes, and we set the value of max accept to the value that the proposer is sending, which is re. So essentially the max accept field captures the value that has been sent by the proposer the last time phase 2 passed. So subsequently the proposal NV is accepted, and V becomes the value of the acceptor, and this is what it uses later on, and it sends a response to the proposer that the proposal has been successfully accepted. So it is important to at this stage understand, and also at this stage realize that this phase 2 will only be successful if no higher numbered proposal has come in the middle. Because if a higher numbered proposal comes in the middle, it will set max prep equal to n, where n is the number of that higher numbered proposal, and thus in phase 2 the current proposal will actually fail. If it doesn't fail, it essentially means that during this time period no other proposal with a higher number has come, and this is a very crucial and important insight which we will be using in the proofs. So we set max accept to V in this case, and which essentially means that this is a candidate for the consensus, right? So it's a two-phase algorithm, which essentially means that this is a candidate for the consensus. So then we send the response to the proposer at the end of phase 2. So the end of phase 2, what happens is that all the acceptors that accept the proposal send a response back to the proposer saying that they have accepted the proposal. If we receive all the responses to the accept messages, so recall that we select a majority of acceptors and we run the protocol with them. If we receive all our responses to all the accept messages that have been sent, then we are sure that the value V that the proposer had proposed, either on its own or because of this line over here, the max of max accept line, we can choose the value V, and value V is the consensus value. So this terminates the algorithm. It's a very simple algorithm divided into two phases, the first phase and the second phase. And if the second phase completes successfully for all the acceptors who are part of the algorithm, the phases, then we declare victory and we say that value V has been chosen. So then what the proposing node can then do is that it can send a message to all the other nodes that look, consensus has been achieved and V is the consensus value. Now here is the fun part. The fun part is that even if the proposer just keeps quiet and uses the value V, all the later proposers are still going to observe value V to be the consensus value, and they are simply not going to observe any other value. So we can sort of say, this, so this is a kind of a very intriguing result. So this is very non-intuitive in the sense, what this is in a sense trying to say is that, well, if I consider my entire system, I ran an algorithm, sent a few messages, and after that, the state of the system has been set to a certain value, such that for every subsequent proposer, if it proposes a value, it is bound to actually choose V. So the state of the system is not going to change, it has been set, and then every subsequent proposer will find V to be the consensus value. So it does not really have to be broadcast. So after the protocol, if somebody wants to just come and learn the value, well, it can ask a few nodes if they are aware of the consensus value. If they are aware, they can send a response. We can always designate distinguished nodes for this purpose, or what the learner can do is that it can simply act as a proposer and try to propose a new value. So if consensus has already been achieved, then the line over here will essentially not allow it to propose a new value. Instead, it will have to propose something which is already there in the system. And if the request goes through, which means both the phases pass, it will choose a consensus value, which again will be V. So as I said, this is a pretty difficult thing to fathom, a pretty difficult thing to visualize. But this is actually true, that after both the phases, regardless of how many proposers come, all of them are guaranteed and bound to choose V as their consensus value. And the crux of this algorithm was a phase 1. So the phase 1 sets a temporary state in each acceptor, which is max prep. So max prep essentially sets max prep is equal to their proposal number. In phase 2, all that they do is that they come and check if max prep has maintained the same value or not. If it hasn't, it means that there is an intruder in the middle, and then they abort. But for any for any sequence of messages where there is no intruder with a higher proposal number in the middle, consensus will be achieved, and the value that will be chosen will be the consensus value. Once consensus is reached, it is reached for all time, and all values chosen will be the same, which is our claim, and we will proceed to prove this in the next few slides. So now the proof follows. So before we explain the proof, let us go through a few definitions. So consider two proposals P1 and P2. So if an acceptor A receives P2's prepare message after P1's accept message, which essentially means, so let's maybe go out and look at this in some detail. So consider proposals P1 and P2. So let us assume that there is an acceptor A, and let this be the timeline. So assume that P1's accept message comes at this point, and then comes P2's prepare message. Then what is clear is that P1 has finished its phase 2, and then P2's phase 1 begins. That part is clear. So we can say that P1 precedes P2. We can have another case at the common acceptor where P1 sends its prepare message. Then what happens is that the prepare message gets cancelled because that n greater than max prep check fails. So this essentially the phase 1 of this fails, and then P2 sends a prepare message. So if P2 sends a prepare message, then clearly there is a strict ordering between P1 and P2. So then also we say that P1 precedes P2. Similarly, we can have other cases where some P3 precedes P4. So this is a standard precedence relationship at a certain acceptor. So if at all acceptors, so it's if at all acceptors P1 precedes P2, we then say that P1 globally precedes P2, but we need not go that far. What we want to now show is that it is possible for P1 and P2 to actually be concurrent. See, P1 does not precede P2 and P2 does not precede P1, then essentially we say that P1 and P2 are concurrent, and concurrency we are depicting by this horizontal hourglass, that P1 is concurrent with P2. So what would be a practical example for that? Well, at an acceptor, what we would have is that we'll have P1's phase 1, and then we will have P2's phase 1, alright, and then P1 will try to initiate its phase 2. So in this case, clearly, there is no there is no precedence relationship between P1 and P2, right? So let's say if this is the phase 1 is the prepare message for them, and phase 2 is the accept. So clearly in this case, there is no precedence relationship. You can't say that P1 precedes P2 or P2 precedes P1. So P1 and P2 both are concurrent. So what we further say is that for two proposals, if they are concurrent at any acceptor, they are just said to be concurrent. So now let's go back to our slide presentation. All right. So we say P1 is concurrent with P2 at A if P1 and P2 don't have a precedence relationship between each other. And at any acceptor, if P1 and P2 are concurrent, then we say that P1 and P2 are globally concurrent. Otherwise, at all acceptors, a precedence relationship holds. So now we'll prove a sequence of 3 theorems which will essentially prove that Paxos successfully achieves consensus. Alright. So let's prove the first theorem, which says that if P1 and P2 are concurrent and P1's number. So recall that we were using the n field in in the algorithm, but we are using num now. They mean the same thing, but this is easier to explain and visualize. So if P1 and P2 are concurrent and P1's number is less than P2's number, so P1, so we claim that for two concurrent proposals of this nature, the one with the lower number, which is P1, that will not pass phase 2 at the common acceptor. So it will not complete its algorithm basically. It will not complete both the phases. So this is easy to prove. So there must be some acceptor that gets messages for both proposals, right? So let's assume that that acceptor is A. Okay. So we will consider two subcases. So the two subcases that we will consider, sorry, one second. Yeah. So the two subcases that we will consider are like this, that assume it first gets a prepare message from P1. So which means that first from P1, it gets a prepare message. Alright, so since they are concurrent, so it will get a prepare message for P2 after that. So since P2.num is greater than P1.num, the value of max prep at this point will be set equal to P2.num. Subsequently, P1 will send its proposal P1's accept message will come. So the first thing that the accept message actually checks is the value of max prep. And at this point, the phase 2 for P1 will fail because the value of max prep has already been set to P2.num, and P2.num is greater than P1.num. So the max prep is greater than P1.num. And this check, which is essentially shown over here, will fail. Because this will fail, P1 will not succeed in phase 2. Let's consider the other case. The other case is we first get a prepare message from P2. Well, so this is even simpler. If this basically says that at this point, max prep is set to be P2.num. Now, P1 sends P1.num as a part of its prepare message. So this will clearly fail phase 1 because in phase 1 we check if P1's number is greater than max prep or not, which in this case it is not. So we see that in both the cases, for both this first case and second case, P1 is not able to pass both the phases, which means that P1 is not successful. Proposal P1 is not successful. So what have we thus proven? We have proven that whenever two requests are concurrent, two proposals are concurrent, the one with the lower number always fails. Right? We can't say about P2 it might be concurrent with something else, but at least P1 will fail, that much we are sure. So we considered concurrent proposals in the last theorem. Now let us look at two proposals where one precedes the other. So if P1 precedes P2, what happens? See, if P1 precedes P2 and P1's number is greater than P2's number, then P2 has to fail, right? P2 will not pass phase 1, P2 has to fail. So this is very easy to prove. We will consider a common acceptor, and there has to be a common acceptor because they send messages to a majority of acceptors. So there has to be one acceptor in common. So that acceptor, what will happen? So since P1 precedes P2, P1's prepare message comes first. Max prep is equal to P1.num. Subsequently, when P2's prepare message comes, we do the same check with max prep, and this will fail because P2's number is less than P1's number. So the check in phase 1 will essentially fail, and P2 will not pass phase 1 because we check with max prep, but P2's number is less than P1's number. All right, so take a look at this. So what have we just proven? We have proven that if one proposal precedes the other, so let's say P1 precedes P2, for P2 to actually pass and be successful, it needs to have a higher number. So if I take the sum total of the last two theorems, they say something very important. What they essentially say over here is that if for two concurrent proposals, the one with the lower number is going to fail. And if proposal P1 precedes proposal P2, then again, if P2 has a lower number, it's going to fail. So in a certain sense, it establishes a certain monotonicity or a strictly increasing order of past proposals. So for proposals to pass both phases, they need to have strictly increasing numbers. All right, if I were to draw a graph, it needs to be strictly increasing. And furthermore, if two proposals are concurrent, then the one with the lower number will fail for sure. So essentially, if I'm an external observer and I keep seeing the proposals that are passing both the phases, I will see an increasing number, monotonically increasing. I will combine the last two results to prove the main result, which is theorem 3. So this says that if P1 precedes P2 and both of them succeed, both of them pass phase 2, then they have to choose the same value. This is the operative part. So which essentially means, so we have already established a monotonicity of the numbers of the chosen proposals, of the proposals that pass both the phases. Now we want to say that for all of them, they choose the same value. So again, we can do the same between P1 and P2, find a common acceptor. So for P2 to succeed P1, well, P2 dot number has to be greater than P1 dot num, again follows from the monotonicity. So now let us set up a mathematical induction problem. So the induction hypothesis is that all the successful proposals with numbers between P1 dot num and P2 dot num choose the value chosen by P1. So if P1 chooses V, all the proposals, intermediate proposals, which pass both the phases, also choose value V. Now, what do we have to prove for the induction to be correct? What we need to prove is essentially that P2 also chooses value V, and this has to follow from the induction hypothesis. So let's see. So the common node A, what did it do? So what did it do is that, so this will come into picture at this point. At the end of phase 1, when those max accept values are being sent, the common node A must have forwarded its value at the end of phase 1 to the proposer of P2, right? So that it has to do, because for P2 to succeed, a value has to be forwarded. So from the induction hypothesis, this value has to be V at the end of phase 1, because that is the chosen value, right? And so this has to be the case. Well, why? Well, the answer is reasonably simple, because this was one of the, why is this the case? Well, you need to understand that A is the common acceptor between P1 and P2, and since P1 chose V, so it must have sent V at the end of its phase 1 to A, such that A would have recorded it, and then A would have sent a response, and this successful response would have been recorded by P1. So the value V that P1 chose must have been there with A, and A must have forwarded this value at the end of phase 1 to the proposer of P2. Right? So this is an important argument to be made here. So now for P2, what would it do at the end of phase 1? Well, it will take a look at all the values that it gets. One of them is V, and if V is the maximum, then there is no problem. P2 will choose V, and we are done, and we have successfully proven. So what we need to prove is that it will never be the case that other than V, some other value is chosen. So let us just assume, for the sake of proving, right, that some value V dash is chosen, which is actually not V. So since a value V dash is chosen, and if we see this, since V is proposed, we cannot choose any value that is less than V. Whatever we choose, since it's a max operation, has to be V dash, and V dash has to be greater than V, assuming we are choosing something which is not V. So in this case, let us assume that let the proposal P3 propose V dash. So by the induction hypothesis, where we are assuming that all the proposals between P1 and P2, not including P2 of course, all of them choose V. So what would be actually happening? All of them propose and choose V. So what would be happening is that there are two cases. Either P3 appears before P1, or P3's number appears after P2. So if P3, let's say, appears before P1, then P1 must have seen P3's value and P1 would not have chosen V because V dash is greater than V. So it is clearly not possible. Alright, so this case is not possible. So the other case that we are looking at, if I were to draw the same diagram, would be P1, a set of chosen proposals, then P2, and then P3. So now let us look at two subcases. Do P2 and P3 have a precedence relationship? Well, if you look at this, it is not really possible because P2 is choosing the value proposed by P3, so they cannot have a precedence relationship. So the only relationship that they're allowed to have is essentially that both of them are concurrent. Now, if both of them are concurrent and P3's number is greater than P2's number, by theorem 2, by the second theorem, we observe that. So what do we observe? We observe that P2 and P3 are concurrent and P2's number is less than P3's number. So by theorem 2, it is patently clear that P2 cannot succeed. But now we know that P2 has succeeded. Since P2 has succeeded, this case also cannot happen. So given that these two cases cannot happen, we have proven by contradiction that we cannot choose a value of V dash which is actually greater than V, which proves that the value that we actually choose for P2 is V, and this proves our induction hypothesis. So just outline of the proof again. Well, the outline of the proof is that if P1 chooses V, and if we assume that all subsequent higher numbered proposals that are totally successful also choose V, we need to prove that P2 also chooses V. So we set up an induction and then we show that the common acceptor must have proposed V. So any value that P2 chose has to be greater than or equal to V. If it is V, no problem. If it is greater than V, then whoever was the original proposer of the value greater than V, which is V dash, either had a number less than P1's number or a number greater than P2's number. Both the cases are not possible. Hence, P2 chose V. So this establishes our induction hypothesis that once proposal P1 is fully successful and the consensus value is V, our previous theorems tell us that no proposal with a number less than P1.num will ever pass both the phases. That is clear. Any subsequent proposal whose number is greater than P1 will of course pass both the phases, but the only value it is allowed to choose is V, right? So that's the only value it is allowed to choose. And furthermore, if I were to consider the condition C2B, when I am computing the max operation, what we have just been able to prove that one of them will at least propose V, and there is no value in the system which is higher than V, which exceeds V. So even the values that will be proposed will all be less than or equal to V, and one of them will be equal to V. So ultimately the values that will be also be proposed will also actually be V, and also the value that will be accepted will be V. Alright, so this has established and we have been able to prove the safety property, which essentially says that consensus is going to hold. So we have not said anything about liveness, which is the progress property. So let's assume P1 and P2 are concurrent, and we will show that there is a scenario where nobody will succeed. So consider P1 sends its prepare message, then P2 sends its prepare message, and assume P2.num is greater than P1.num. So then P1 comes with its accept message. The accept message will not pass phase 2 because of intervening P2, so it gets failed. Then the proposer of P1 sends P3. P3's prepare message has a greater number than P2's prepare message. So then P2 sends its accept. The accept again fails, and then so on and so forth. Then P2 sends a P4, and P3 fails, and P4 fails, and P5 fails. It is possible we might have an infinite sequence of such kind of failures. So at the end, no proposal will succeed in both the phases. And because of this infinite chain of failures, we'll theoretically never achieve consensus. So this is clearly in line with the FLP result, which says that we will always find some sequence of actions where consensus is not achievable. But again, liveness was not our aim, because we knew that both safety and liveness are not simultaneously enforceable. So one way is to, of course, eliminate concurrent proposals. We can use a leader who is only allowed to propose. Similar ideas have been taken up by later consensus proposals to simplify things. Of course, we still cannot find a way around the FLP result, so no point in trying. And but at least Paxos provides safety, right? Just in case anything happens, so Paxos still provides a certain degree of safety net. And furthermore, the idea now is that Paxos is complex. So why is Paxos complex? Well, because this was a protocol for accepting a single value. But let's say that we want to send a sequence of values, like a sequence of transactions to different servers. Then essentially all the servers have to agree on the sequence of values. So we will have to run multiple rounds of Paxos. So this makes things very complicated. And that is where other consensus protocols will come in, which are simpler and simpler than Paxos and provide more elegant solutions. But nevertheless, Paxos still remains one of the most popular and one of the most widely used and widely discussed consensus protocols, maybe the most popular. And anything else, any other later consensus protocol, use Paxos as a gold standard for comparison. So the original Paxos paper was published in 1998, which was reasonably long and reasonably hard to understand. So what we have presented in this lecture is Paxos made simple by the same author, Leslie Lamport, which was published in 2001. So in subsequent lectures, we'll discuss other kinds of consensus protocols, which are simpler and which are specialized to certain application domains.